So Cody can hear us, which is great. When during the year, it's really important, I believe, that you buy the Massa Revision Guide for Maths Methods. What you'll need to do is when it is published, either the end of this term or beginning next term, just to get one straight away. They don't produce a huge number, so it's first in, first served. So I'll try and give you another reminder as soon as I know that they're published. They cost around $28.50. So I've got weekly work from some of you, so well done. Um, how are people going with the weekly work? Let's just do a little continuum. So I'll just make a new whiteboard. So because we've got a test coming up pretty soon, and one of the things that is extremely important for all your stage 2 subjects is if you're up to date. So I want you to do, where's my text? Not up to date, and up the other end is confident or up to date. But I want a second one. I want one that is confidence. So are you understanding it? Thank you. Oh, well, I'm not ready yet. Oh, try again. All right. So there's two questions there. One is whether you're doing the work and up to date with it. The other question is whether you have got it, whether you've done enough of the work to feel that you've really confident. Because week 6, we're in week 4 now. In 2 weeks' time will be the first test. And what happens is in week 6, you'll be learning new work. So there is no stopping. There's no like week for revision. So let's just see how you two are feeling. So Hannah's saying that she's up to date with the work but the confidence is in the middle there because she's making silly mistakes. And I sort of like the word silly because a little bit more practice, a little bit more confidence, and they'll stop. Do you have any advice for each other for reducing those sorts of mistakes? Thanks, Hannah. Yes, writing neatly and setting out your page neatly. Do you know what? Very often, if something goes wrong, it goes wrong in the first couple of lines. Now, that's not always the case. Um, I'm fine when you get on to applying your knowledge with differential calculus, quite often a, a narrow, like 2 columns to a page becomes too narrow. So please, who is willing to sort of have some blank space on their page and not use every little bit? So I advise spread out your work, which is a follow on from Hannah's comment. Now I haven't seen, yeah, I've seen an arrow there. So I'm not seeing the weekly work, and usually that means it's not being done. I want to advise you that if the week is nearly over, just show me what you've done. Um, and I don't know whether cut your losses is quite the right idea, but adjust the amount you do so that you are keeping on with the new work. It's better, I believe, to do just a little bit less than is set and keep up rather than be a whole week behind because then the lesson lacks meaning. What I'd like you to do now is on your own piece of paper, work out this question, and I will quietly write up on the board as we go. So hopefully you'll be a bit ahead of me. So this should be work that you're confident with. So maybe I better ask, who is confident to get going on this question? Cross if you're not. All right, Hannah. Well, see if you can do it again on your own, but I'm going to talk to it for the benefit of other students. So, when you look at this question, there are two unknowns, the A and the B. So, my immediate thought is I'm going to need two equations and solve it simultaneously. I'm given the information that at the point 3, 1, when x is 3, y equals 1, the gradient is negative 1/8. So let's just put in that very first bit of information. If I put into the original equation when x equals 3 and y equals 1, I'll get the equation ah, 1 equals. Now, I'm going to write this with a negative power. So a stays there. The square root of 1 plus bx is minus a half. X was 3, so that's 1 plus 3b. So I'm going to rearrange that so that A is the subject, because I'm suspecting that in a minute I'm going to substitute into a second equation and eliminate the A. And so that negative power becomes a positive power. A will be 1 plus 3b to the half. When I look at the gradient being negative 8, I realise I'll have to find the derivative. So y dash, so make sure you label it correctly. I'm going to take the derivative, maybe if I just write it up the top because I've got a lot of space. When you write down the question, I highly recommend that you write it with fractional powers. So when I take the derivative of that, a stays out the front. Now, I'm going to use the chain rule in my head. 1 minus bx, I'm just going to hold that there, like the u function. I'm going to use the chain rule. I'm going to look at the power, minus a half. And I'm going to take 1 from the power. Minus a half, take 1 is minus 3 on 2. And then the chain rule part is to take the derivative of this function, 1 minus bx. That's just going to be minus b. And now I'm going to put in the information I was given, that dy dx is minus 1/8. A lots of minus a half times minus b is just going to be a half out the front, becomes positive, ab. Now we know that this occurs when x equals 3, the gradient of minus 1/8. So I'm going to put x equals 3 in there. So instead of x is 3, so that's minus 3b to the power minus 3 on 2. And that's my equation 2. So I'm going to substitute equation 1 into equation 2. So a is 1 plus 3b to the half. Actually, I multiply throughout by minus 8 first to get rid of the negatives. So that will be 1 equals a half times minus 8 will be minus 4. Hope I haven't made a mistake. I think I have. All right, I'll keep going. If you've noticed I've made a mistake, just point it out. Ooh, all right, Hannah, I've just read your text chat. We'll just have to give you some practice a bit later. Now, I didn't, I'm doing this in two steps because I'm simplifying by multiplying by -8. And now I'm going to substitute for a. So the a up the top here is 1 plus 3b to the power half. And so that's a. The b's still there, so I'm going to squeeze that in front. And now this is where it's looking complicated. But you notice 1 plus 3b is the same base. So 1 plus 3b to the half times 1. Oh, is it plus or minus? Oh, I've made a mistake, I'm sure. See, all right, this is problem solving. Let's look back and just double check because I want that base to be the same. So I think there's a mistake there. Let's have a look. That's a plus, that's correct. So this here should be a plus. Smart, agreed, everyone? So just give you a minute there. That should be 1 plus 3b. So these should all be pluses. Okay, now it's got the same base. And a half plus minus 3 on 2 is just -1. So the minus 4b out the front. 1 plus 3b to the -1. Now, you can picture that. That's actually on the denominator. If we multiply both sides by 1 plus 3b, that would come onto the left-hand side. Now, I'm running out of space, so I'm going to multiply both sides by that and get rid of the negative power. So I'll have minus 4b equals 1 plus 3b. So if I take 3b from both sides, minus 7b will equal 1. And therefore b, oops, b will equal minus 1/7. Now, I've got a feeling from the answers that that is not the correct answer. So I'm going to stop there. But can I have a smiley face? Can you see the method even if I have made an error in the working? So this is showing you the standard required of it's making assumptions that you remember your year 10 maths where you did substitution, that you're confident with fractional powers and with negative powers. So all of that knowledge comes together, and time and again, you'll end up with something that looks very complicated, but when you look closely, if you haven't made an error, it will simplify. All right, over to you guys again. Can I have a tick if you're very confident just to practice using the quotient rule, and a cross if you're not so confident? So those that are confident, Hannah, would you please just quietly work on your own and I will talk through this one. Thanks, Hannah. When you look at the quotient rule, the main thing is to get confident enough to do a lot in your head. But in the meantime, the, the numerator function, the root x, we normally say let u, and u is a function in terms of x, equal, and I would immediately write it as a fractional power. And if you look at the quotient rule is going to find the derivative of the u function. So I would immediately find the derivative of the u function. That's going to be useful in a minute. So half x to the minus a half. The v function by habit is the denominator function, and that's going to be 1 minus 2x squared. And this is where being able to do the chain rule in your head is very useful. So let's just do that. Let's immediately find the derivative of the v function. So you look at the 1 minus 2x and you just write it like a subfunction. You look at the power of 2, so you're going to multiply by 2 and you're going to take 1 from the power, so it's to the power 1, and then you're going to do the derivative of this function 1 minus 2x, which is simply minus 2. And then, taking on Hannah's advice, you're going to rewrite that a bit neatly. 2 times minus 2 is minus 4. And the power 1 we don't normally bother with, so you could possibly multiply that out. Doesn't really matter. So now we're ready to use the quotient rule. The quotient rule up the top is the derivative of the numerator function, so that is a half x to the minus a half, times by the u function, unchanged, which was just x to the half. Subtract. The quotient rule is subtract. A lot of students, they make a mistake. Then, I've made a mistake. Anyone notice? The pattern is the derivative of the u function multiplied by the v function. So that was not the denominator function, that was the numerator function. So let's fix that. The v function was 1 minus 2x all squared. Subtract. Now, the u function unchanged is x to the half times the derivative of the v function, which is minus 4. And I'll just put that in a bracket so that it's clear we're multiplying. 1 minus 2x. Then that's all divided by the denominator function squared. So 1 minus 2x is already squared, and we square it again, it's just to the power 4. And again, people tend to forget when they're not confident to square the denominator. Now, that could be simplified, but there's no point. This is just a skills practice. Just show that you know the quotient rule. And if you had to use the quotient rule to find the gradient function, and you were told to find the gradient when x equals 0 is a nice one, but when x equals 1, it is just as easy to substitute a value of x into 1 in this complicated, unsimplified function. So you don't need to bother to collect like terms and simplify and multiply out brackets. Any questions with this problem? Okay. Matt, just waiting on you. You might still be writing it out. All right, thanks, Matt. Okay, so that was a very quick revision of where I hope that you are up to with your work. And now we're going to look at differentiating exponential and log functions. So my first question to you guys, when you look at this whole set of exponential functions, is there anything you notice? So hands up, and if you've got a comment and then someone else has a comment, please ask the next student. Oh, yeah, all right, off you go. Thanks, Hannah. Anything more? Any more comments? Where? Is there anything about that horizontal asymptote? Can you name it? Actually, x isn't 0. If I plot that point is 1, 0, and this point, that's it. Thank you, Hannah. Now, is there any, noticing that the horizontal asymptote is y equals 0, is there any extra thing that you notice about the values of all those exponential functions? None of those exponential functions has a value below the x-axis. That means that all of those exponential functions are all greater than 0 for all values of x. What happens if you put a negative value in for x? What happens to the exponential function? Let's have a look. Let's look at this green function. I've gone crooked. Fx equals 2 to the, oh no, that's not a negative x. Actually, this set of functions is only for positive x. Um, what happens when the base is less than 1? Matt, what are you thinking? What happens to the function? Here the function's greater than 1, 5, 2, 1.2. That is greater than 1. What happens when the base is less than 1? 0.2 is less than 1, 0.5 is less than 1. Can someone help? Excellent, Matt. Can someone suggest a word that's going to help Matt out? Hannah? Um, no, they're not inverse functions because an inverse function would be a reflection in the line y equals x. And what happens is that the x coordinate becomes the y coordinate. That word flipped, is there a better word than flipped or a more precise word than flipped? And flipped around what? Cody, do you want to text chat something seeing your mic's not working? And Reese, have you got a comment there? um, or I'm not, if it was spun around, let's go green. If it was rotated, it would need to be rotated about, well, I'm going to rotate it about this point, 0, 1, the y-intercept. If I rotated that curve 90 degrees, do people agree if it was spun, which is a rotation? This is tricky. It's partly language, it's partly spatial skills, which apparently boys are better than girls. So, Reese, if it's not rotation, or something, flipped, the other word to flipped, Matt, is reflected. Reflected in what line? So please, to get ideas off of each other, can you remember to change to all participants? And if I said it was reflected in the y-axis, which is x equals 0, do you agree? Let's stick with this green function. Oh, let's go to the red one. Can you see this red function? If it's reflected, um, it's reflected, if it was, it would come this way. Okay, so there are just some things to notice. Yeah, inverse function. Actually, the logs are the inverse functions, which we're coming to. So keep that thought, Matt. So if I just summarize what you guys have noticed, you've noticed for all the bases greater than 1, no, all of the x values greater than 1, all the positive powers, that the functions are greater than 0 and that they all intercept the y-axis at the point 1. And there's the basic shape of increasing at an increasing rate. So if we looked at the gradient where it's asymptotic to the x-axis is close to 0. And then if we keep on taking the gradient, it gets steeper and steeper and it approaches positive infinity. So the slope is increasing along the function. So people started to play games. Now, have you guys used Desmos? Do you want to just Google Desmos and try and do the same as me? I'm going to um, share my Desmos graphing tool, but you guys might like to do the same. It's a bit of fun. So, oops. So I'm just going to select. It's not turning off. All right, just have a look. I have drawn the function y equals 2 to the x. And if we take the derivative of it, that light blue function appears. Anything you notice about the shape of the derivative of the exponential function 2 to the x? Is it a linear function? Is the derivative a linear function? All right, do you agree with Hannah? It's not a linear function. Is the derivative, is this blue function, is it a cubic function? And you might recall that a cubic function is in the form, oh, I can't draw on this. I don't know if it'll let me. All right, a cubic function is in that form. Haha, definitely not linear. Excellent. Could it be another exponential function? What do you think? Does the shape look like another exponential function? So when people noticed that, they thought, gee, wouldn't it be interesting if I could get a base so that the derivative of that base was the same function? So if you fool around, so I'm just going to turn off those. So instead of having a fixed base of 2, I've got the letter A, which I can change. I can start with A at 2, which we've already drawn, and do the derivative of it. Or watch what happens when I change the base. Can you see that the original function changes? Let's start again. All right, let's try again. So the purple function is the derivative, and the green function is base 2 to the 1. Do you see that the base function moves up steeper, but so does the derivative function? And there's a point approximately 2.7 where the derivative of the original exponential function is identical. Is that cool? Do you think that that's a bit of an intriguing property? Well, mathematicians did, and they called that, so that is a special exponential function. So there's a set of exponential functions, right? A base number to a variable power. There is a special exponential function with a number very close to 2.7. Does anyone recognize that number 2.7? All right, Hannah, do you want to share what you recognize? All right, if you've got your graphic calculator nearby, let's just practice finding E on your graphics calculator. So what you do is you type E to the power 1, and do you want to text chat what value you get? So if you've got your graphics calculator out, we'll just put it in the normal run menu. What we want to do is the exponential function e to the x, so shift, choose the yellow e to the x, and e to the power 1 will give us the value of e, 2.718. Yeah, excellent, Hannah, you're quick off the mark. So just give the others a chance to practice finding the exponential function, the special exponential function. So that's what people we talk about the exponential function meaning E. E is just a number. It's an irrational number. As Hannah has shown, the decimal is no pattern and it goes on forever. So we can't write 2.178 2818 every time. So we say let that be represented by the letter E. Now there's a second fun thing to do. It was also found out that 1 plus 1 on the variable t, when t approaches infinity, that also gets the value 2.178. So this number, 2.178, is intriguing and it reoccurs. So that's where we get the value e from. It's a special number, it's an interesting number, and we label it with the letter E. So we've just established that the derivative of e to the x, so if y equals e to the x, we've just shown that the derivative is also e to the x. So if we are to find the derivative of this function, which really should be written y equals, then y dash will be, derivative of a constant is 0, minus 2 is a constant, so we'll put that out the front. The derivative of e to the minus x is itself, e to the minus x, but minus x is a function in its own right, so we take the derivative of minus 1. The derivative of minus x is minus 1. And normally we would say minus 1 times minus 2 is 2e to the minus x. I'll give you a moment. I hope you've got the... Oh, that is interesting, Hannah. Um, I lived in Western Samoa, and as an Australian or a South Australian, the word cheeky meant a little bit naughty, but basically funny. Oh, it didn't mean that in Samoa. It meant you were naughty and you had to be very careful. So the use of words is very interesting. Thank you, Hannah. All right, everybody, can you give me a tick? Are you confident to use the product rule? Tick if you're confident, cross if you're not. Aha, excellent. So I'd like you people to have a shot at part B on a bit of paper, smiley face when you're done. And just remember, when you're done, might means I'm stuck and so I want someone to go through it. Now, Hannah's question, this is what you've got to internalize. When you differentiate e to the minus x, you get e to the minus x. That's what we've just shown. We've shown that we've got a special base, the base which is the value 2.17, so that when you take the derivative of it, you get another one. It's great. You got to take it in. The only caution is that e to the minus x, I'll just do this on the side. When you take the derivative of e to the x, you get itself, and if you take the derivative of the function x, which is just 1 times x, it's multiplied by 1. So as soon as you do the function e to the minus x, you've got to take the derivative of the power, and that's how you get the negative. So can I have a smiley face if you've finished part B? Yes, that's what I want, Hannah. Give everyone, can you give me a tick or a smiley face if you understand what happened in finding the derivative of x cubed e to the minus x? Yeah. All right. Now, you've only just begun to see the derivative of e to the x, but I'm going to go on and touch base with... Oh no, let's do a slightly harder one, and then I'm going to touch base with the inverse function. So if you can do it ahead of me, do so. Otherwise, I'm just going to write this one out. So as I said, I recommend that you immediately write it with fractional and a negative power on this one. So that's going to be 2e to the minus x plus 1 all to the minus a half. So if I take the derivative of that function, I'm going to do the chain rule in my head. I'm going to look at 2e to the minus x plus 1 as a u function, and I'm just going to hold it in my mind. So I'm just going to write it down, and then I'm going to use the power rule. So the minus a half comes to the front, and I take one from the power, so I get minus a half minus 1 is minus 3 on 2. And then I've got to take the derivative of that function, 2e to the minus x plus 1. Well, that is going to just be 2 is a constant in the front, e to the minus x. The derivative of e to the minus x is e to the minus x, but the derivative of the power is minus 1. So I'm just going to put a minus 2 in the front. And just to show that it's multiplied, I'm just going to put brackets there, because the little multiply symbol and the variable x can easily be confused. So using brackets, I think, is a neater way of showing that they're multiplied together. So really, we're done. And you don't really need to simplify any further. You might wish to. You might say minus a half times 2 times minus 2 is positive 2. So you might just write it 2 e to the minus x plus 1 e to the minus x. All right, so tick if you follow the reasoning, hand up if there's something that you didn't follow. Not quite sure what you mean, Hannah. Hannah, I've probably told this to you 2 years ago that I have German heritage, but it's a very long way back. What are you saying about the Germans? Thank you, Hannah. Now, have I missed a slide? What I want you to realise, so I just need the whiteboard for a second. Are you able to draw an exponential function? Have a little go on your bit of paper. And what I hope you're thinking is, all exponential functions are going to intersect the y-axis at 1, yes, thank you. And you're going to try and draw a curve that is asymptotic to the x-axis whose equation is y equals 0 and whose slope is increasing. Now, as you were talking before about inverse functions, if we reflect, it's good if I have a dotted line, but I don't have that ability. If I reflect in the line y equals x, we'll get an inverse function. So if we just look at the point 0, 1, and you invert the order 1, 0, we're going to get what is end up getting called a natural log function. The natural log function is asymptotic to the vertical y-axis. So those points 1, 0 and 0, 1 on the exponential function become very important. So the natural log, so this is meant to be e, that's meant to be an e to the power x. That's not very neat. Ah, drats. I can't undo it. Okay, so that's the natural log ln of x. So immediately have a race in text chat. What is the value of ln1? Yes, it is 0. All right? When x equals 1, the function ln x, so that when I put in 1, I get the y value, which is 0. And the thing about an inverse function is the inverse is going to bring you back to the identity, which is 1. So, or the original. So if I do ln of e to the x, then the ln, the original value x, where you take it to the operation of exponential and then you do the inverse operation, which is natural log, you get back to what you start. You get back to x. So that's the natural log is the inverse of exponential. Now, I seem to have missed out a bit of theory. I just want to see if you're able to open your own ebook to page 48, would you do so? I just want to use that animation. I will also do the animation. I just want to show you that when you find the derivative, now how am I going here? When you find the derivative, is that going to work? Oh, here we go. This is a little interactive that gives you the natural log function. So just identify we've got an x-intercept of 1, 0, and it's asymptotic to the y-axis. All right, so there's our function y equals ln x. This table will show how if we change, oh, sorry, I'm looking at the table and there's the original function, which we've just drawn, and then there's a derivative function on the table. So remember the derivative is a function that finds the gradient, and the gradient at a fixed point is just a fixed value, but a function of x will find out all of the gradients. So let's have a watch. So just have a look at this point here. The gradient is approaching 0. And so the function, so this, if I go back, the gradient began at a high value. It's a bit quick for me actually. Um, there we go, that's better. So the gradient began very steep and the gradient changes and it actually approaches 0. So does anyone recognize the shape of this function down the bottom, which is the gradient function, which starts with high values and then ends up with values approaching 0? Yes, Hannah? It's actually the inverse of x. It's 1 over x. I'm not sure how, this is knowledge that is very important that you build up. Are people aware that most rational functions or quotient functions, so that's the same name for the function, often have two parts like that? Can you give me a tick? Are you aware that quotient function, so u of x on v of x is a quotient function or a rational function? That in general, they've got asymptotes. Okay, well, this is something you've got to build up your knowledge on. And All right. I recognise that it's 1 on x. So when it's just the positive bit, it's 1 on x. So when x is greater than 0, that function is 1 on x. So the derivative, remember the derivative is the slope function, the derivative of the natural log function is 1 on x. So I'm going to stop sharing. I'm not sharing. Sorry, everyone, I've got lost. So I'm not sure if I was sharing when you, with the textbook. Did you see what was happening on the textbook? Thank you. I must have accidentally hit the wrong button. Um, so, so now I'll just do one practice and then I must stop because all of us probably have another lesson. Find the gradient. You're just going to use the knowledge that the derivative of a natural log function is 1 on x. So, if I look at part A, the derivative of ln kx is 1 over kx. But then I've got to take the derivative of the kx, and that's going to be on the numerator. That's just going to be k. Now, so long as k is not equal to 0, that will cancel. So y dash will equal 1 on x. Let's do part B. Y dash. So it's going to be 1 over the function. The derivative of natural log is 1 over the function, 1 minus 3x. So long as the function is a linear function. I better repeat that. Notice that 1 minus 3x is just a linear. X highest power is 1. So just the 1 over the x or 1 over the linear function. And then I take the derivative of the linear function, which is just minus 3. So we're going to multiply the numerator by minus 3. And there's no need to simplify in any way. So get really confident with the exponential functions first, and then you're going to do things like part C. Now I've got to end very quickly here. We're in week 4 at the moment. So on Sunday night, I put up week 4 work. Glad you're back, Matt. And please notice that next week, week 5, in the Moodle, we'll put up a practice set, and a couple of days later, we'll put up the solutions so that you can learn from marking your own. But in the meantime, gee, I can't remember because we did this end of last year. I've got to double check. We're going to start second derivative next week, and I'm unsure where the second derivative is in. So I'll have to send that in an email, what is included in the test. So the test is not until week 6, but if you're a little bit behind, you've got to catch up because the test will focus on application. So SAT stands for Skills and Applications Task. So during lesson, I haven't done a lot on application because you've got to get the basic idea before you can apply it. But the weekly work, have you noticed? Give us a tick. Have you been doing some of the applications successfully in the weekly work? Excellent, Cody and Hannah. All right, and Matt. Excellent, Reese. All right, everyone. Can you say goodbye to each other? Have a great week.